This lesson is on definite integrals and area, and in the past few lessons we've been talking about the fundamental theorem and just how to do it algebraically. Now we're going to talk about where that actually helps us, and that is for figuring out exact area. So the first thing I wanted to remind you is that if we have this integral from 0 to 4 of 4x minus x squared, which would have a graph something like this, we are actually finding that area between that graph and the x-axis. So again, that's what that means, and that's the purpose of what we're doing here. Okay. As I mentioned the other day, sometimes it is easier to use geometry to figure out these areas, and so I have a couple of examples of that to start out with. The first one is we have the integral from 1 to 3 of 4, and so if I have the graph of that, it's just a horizontal line, and because that's like y equals 4, which is your horizontal line. And so we were looking at the area between 1 and 3. So just from here to here, this area. Okay, and so that's just a rectangle, and that's really easy, just base times height. The base is 2 units wide, the height is 4, so we have 2 times 4. And so our answer is 8 there. And you could do the fundamental theorem and you would get 8 as an answer, but that one's just really easy to do with geometry and thinking about it. Another time that geometry is pretty easy is when you have a line. And so this is the equation of a line with a y-intercept of 2 and a slope of 1. So if we look at the graph of that, it's pretty simple. And again, I'm doing the area from 0 to 3 this time, so 3 is that last part there. I'm looking at all this. And in geometry, that is your trapezoid. This one happens to be turned sideways from what we're used to looking at in regular geometry classes. But our area formula is 1/2 the height, which now is on your x-axis because it's laying sideways, so that would be 3. And base 1 plus base 2. That first base is 2 and that last base is 5. And so if we calculate that, you get 21 over 2, okay, is I just like my top heavy fractions, so you could have used the decimal form of that as well, but that's a really easy calculation, geometric. Now, before we do our next one, I want you to remember about the equation of a circle. The equation of a circle, x squared plus y squared equals r squared, is your basic equation. When it gets shifted, these become like parentheses, x minus 1 or y plus 5 or something like that. But if we take that generic equation where it's centered at 0, 0, and we solve that for y, we get y to be the square root of r squared minus x squared. And to be a function, we're just going to look at the positive square root, because if we looked at the positive and the negative, we would be looking at that circle, and it would not pass the vertical line test. So example 3, when you look at it, you may think, okay, this is u sub, or maybe this is related to an arc trig antiderivative, but it's actually the equation of a circle, and so it's going to be simpler to do it geometrically than it is going to be to try to do it with rules, because this one really gets kind of nasty if you're trying to use rules. So we'll look at the graph of this from -2 to 2, and we should just be looking at the top half of a circle. Okay, so when we graph this, we have the top half of a circle, and since this was a 4, and if you look back up here, that first number is r squared, that means our radius is 2. And so it makes sense that they're asking us to do from -2 to 2, because that puts our center at 0, 0 and our radius to be 2. But again, I want to find this area, all in here, which is half of a circle with a radius of 2. And so your area formula for a circle is pi r squared, but I want half of that. So 1/2 times pi r squared. And like I said, our radius is 2. And so if I square that and multiply by 1/2, I get 2 pi, or whatever that is as a decimal. But again, that was a really easy geometric calculation compared to the algebra you would try to get into otherwise. Okay, so example 4, we have another line. This is a good one for you to pause and remember how to graph, but I need to show you something about the area that's a little different this time. So if you want to pause and try to graph it, you can. I'm going to continue on. Okay, so when we graph the line y equals 2x, we have a y-intercept of 0 and a slope of 2. And so since I'm looking at it from -2 to 1, this is the part of the graph I'm looking at. Well, everything that we've dealt with up until this point has been above the x-axis. So for this part, from 0 to 1, I'm definitely looking at that area. But this is the first time we've had anything below. Well, it's still the area between that graph and the x-axis. So we're looking at this area in here. Now, what happens when area is below the x-axis is that it is considered negative. And this is how the other day I said, you know, it's okay to get a negative answer. It does have meaning. This is what it means. It means that that area is below the x-axis. So it's a triangle shape, and again, that's easy to calculate, but what we have to do is remember to put a negative with that. So for that first triangle, I'm going to say -1/2 base times height, and our base is 2, and our height is that distance 4. So I just make sure that whatever that calculation is for this triangle comes out to be negative. But I am adding it to a positive area, and so since this is a smaller amount of area than this, we should get a negative overall answer, but you do consider this part positive, so plus a +1/2 base times height. And so if I cancel the 2's out and multiply here, I get -4, and then 1/2 times 2 cancels, so this is 1. And I do end up with the area of -3, just like I suspected, because, again, this was more negative than this was positive. So that's something to learn from this problem. You may want to put a star beside of it. Okay, so before we move on, I just want to go to a generic kind of situation about this positive and negative area. Just kind of draw some kind of wavy graph here. And I'll make something up. Let's say that we know that this area, and I'm not sure why it's disappearing, know that this area is 2, this area is 3, and maybe this area is 6. Again, I'm just making this up. If we're adding those together, once we figure them out, the 2 and the 6 are considered positive, but the 3 would be considered negative. And so you would end up with a total area of 5 if that's what we were looking at. So again, just keep that negative area concept in mind. Now, before we go on to some more examples, I also want to remind you about what it means to be an even function or an odd function. And I have the most classic examples here. For our even function, I have y equals x squared, which is your parabola. Even means that I can fold it on the x-axis graphically, and it land on itself. So it's symmetric with respect, to the y-axis, not the x-axis. To the y-axis, I can fold it right there and it lands on itself. That's even. And those typically have even powers. Now, if you have something with an even power that's shifted left or right, you're not going to be able to fold it on the y-axis. So that's not a completely even function. Odd, I have your y equals x cubed graph, and odd has rotational symmetry, meaning I can turn it about the origin, 0, 0, and if I turn it, this part that was up here is going to land down here, and then the part that was down there is going to land up at the top. So it's going to land on itself, turning it 180 degrees. And there were rules that we studied in pre-calc for this, but you don't have to have them memorized. You just have to really kind of understand graphically what's going on. I have a couple of other examples, trig functions. This is another even trig function because we can fold it on the y-axis and it lands on itself. This happens to be cosine. And again, if you just imagine folding it, it will land on itself. This graph is odd, and it happens to be sine. And again, if you notice, just take even the first part of it. If I take that part and I rotate it 180 degrees, it's going to land right here on itself. I have to turn around the origin. So again, that's how I know it's odd. So those are not every function, but those are the characteristics to look for when you are determining whether things are even or odd. The next thing we're going to go over is properties of integrals. In other words, these are things that you can do to manipulate the problem and make it a little easier to solve. Some we've already been doing. We already do this first one with U substitution. If you have a plain number times the function, you can bring that plain number out front. As long as there are no variables with it, it's good. So that is something that you should already be familiar with. Also, and we've done some things with this in it as well, if you have two things added together or subtracted, you can look at their two integrals separately. And I think in something we did recently, we had something like 1 plus sine of 2x. We'll say that that was that. If you look at the 1 as f of x and the g of x as being the sine of 2x, you could do that integral separately. And that would be a good time to do that because this is going to be a u substitution, but the antiderivative of 1 is just x. So that would be a really easy part of the problem to do, but this part could be u sub and may take a little bit more to get done. So that would be a case when you would want to separate them. A couple more. We have this one. First one I call kind of common sense one, the integral from a to a of f of x dx. Well, if you remember that it stands for area, if you're going for the area from a number to itself, like the area between 2 and 2, you haven't got any area accumulated. It's just like a straight line, which doesn't really make sense. So that area is 0 if the limits are the same. And also, if you think, this one down here, if you look at these limits, they're all f of x. So from a to b plus from b to c is the same as a to c. And so if you think, again, graphically, what we're saying is the area from a to b plus the area from b to c is the same as the whole area from a to c. And so again, that's kind of, it makes sense. Type of property. This last one, I want you to put a star beside of. This one comes up some in our manipulations and algebraic computations. If our limits are over here, you should always have the lowest limit in the bottom spot and the highest limit in the top spot. And I have made a typo here. So let me pause and fix that and then discuss that. Okay, so now I've fixed my typo. I have the limits from b to a. Now I switched them, which makes, if we look at an alphabet, a comes before b. So a should be actually lower than b, and we have it backwards. So in other words, if your limits are backwards, what that means is you need to put a negative out front and switch those back to normal. Okay. And I'll do one of those as an example down here in just a minute. So again, the limit should always be lowest to highest, and if it's not, you switch them and put a negative out front. So let's look at examples of some of these properties. Alright, for example 5, we have the limit from pi to pi of sine x dx. And again, since these two match, there's no area accumulated under there, and so that would be 0. 6 is what I was just talking about up there. There's that last property. Here I'm going from 3 to 0, but I'm supposed to go from 0 to 3 because I always go from low to high. So I have to consider that as the negative integral from 0 to 3 of x plus 2 dx. And I used this particular one because we've already calculated that in our area problems where we were using geometry on up in your notes if you want to look back. We know that area is 21 halves, So the negative comes along outside, and then this area, again, I've already done that calculation, is 21 halves. So this makes a negative 21 halves as my answer. But again, notice those limits and then changing it by pulling a negative out front. And then we have example 7. So here we have the area from 1 to 3 is 7. The area from 3 to 5 is 2. What is the area from 1 to 5? And sometimes I need to picture these. These obviously are easy numbers, but it kind of helps me if I draw a little number line. I'm talking about 1, 3, and 5. So here I have the area from 1 to 3, I'm going to say is 7. The area from 3 to 5 is 2. So what is the area from 1 to 5? Obviously that's going to be 9 because I just have to add those together. And so it helps me to draw those things out. 8 is another example here. I have 0, 8, 5 as my points of interest, so I'm going to go ahead and list those. And it doesn't have to be perfect, it's just for my thought process. So I know that from 0 to 8, my area is supposed to be 10. From 5 to 8, that is negative 1. So technically I could have drawn that down here. What is 0 to 5? So if from 5 to 8 is negative 1, and I have to add up to be 10, what does 0 to 5 have to be? And that would be 11, because 11 plus negative 1 will equal 10. So if I were really looking at the graph, from 0 to 5 should be a positive area, and from 5 to 8 should be a negative below the x-axis area. But here, this is just my scratch work, so nobody's going to look at that and say, well, you didn't do the right shape or whatever. As long as you understand it and can make the numbers add up right, you're good. So you don't have to do that. Some of you can just do that in your head. Whatever works for you when you're doing problems like 7 and 8. So that concludes this lesson.